LR circuit is similar to a mass falling in the air friction. And then think about even the equation for the energy stored in an inductor, half Li squared. And then the energies of the battery, all of these equations, right? This one, energy of a resistor, energy of an inductor. And then these ones, these last two are the LC circuit. Okay, so that's kind of what we're going to end with. Even think about the equation, U is half Li squared. Where is that coming from? Right? U is equal to half Li squared. Well, what is its mechanical equivalent? Energy is equal to half. L is replaced by M, and then I is replaced by V. Oh, it's actually kinetic energy, right? So the energy inside of an inductor is in the form of a motion kind of energy, where the magnetic field flowing through the current flowing through the inductor creates magnetic field, and it behaves like the kinetic energy that a falling object has, that a moving object. So that's the analogous physics 101 analogy. Okay, so now let's do the LC circuit. So you have a battery, inductor, and then capacitor. Right, and then that would be a charging LC circuit. And then if you don't have a battery, you just have an inductor and a capacitor. Let's say you have a charged capacitor, and then you connect it to an inductor. So then what is that like? This is like without a battery, right? So what would their physics 101 equivalent be? This one would be, remember when you have an inductor, it's like having mass, and then a capacitor is like having a spring. And this one is like having a weight. So it'd be wall, spring, and then a block, right? So then what is this one gonna be? This one's gonna be more like this, a wall. I stretch the spring, right? I stretch the spring, and then I let go, and then it goes back and forth. So the reason that it doesn't have any battery means gravity is acting this way. So it's not giving it any stretch. The gravitational force is being neutralized by the normal force. So they cancel. So it's just basically oscillating between the potential energy of the spring and the kinetic energy of the block. This is also oscillating between the potential energy of the capacitor and the kinetic energy of the current flow through the inductor. You see? Now, how is this different? This one is gonna stretch because of gravity. It's gonna stretch because of gravity. And the stretch amount is gonna be what? mg over k. But on top of that, it's gonna oscillate around that new stretch position. So that's the position of the object is gonna go back and forth around that new stretch position. Now this one, it will go back and forth around the natural equilibrium length of the spring, you see. So it's not gonna have any certain amount of stretch amount. But this one is gonna stretch, then it's gonna oscillate around that stretch amount. So I could actually come up with the equations of motion of this guy, then I can go back and do the equations of that. So now I'm working backwards to cheat, you know. So the motion of this is going to be A sine omega t plus phi. V is equal to A W cosine of omega t plus phi. So this is again from Physics 101. And A is negative A omega squared sine of omega t plus phi. And omega is equal to square root of k over m, where k is the spring constant, and m is the mass of the block. And then the period of the motion is 2 pi square root of m over k. This one is going to have an extra stretch amount. So it's going to be mg over k plus a sine of omega t plus phi. A is some stretch amount beyond the new equilibrium position. This is the new equilibrium position. So then V is going to be the derivative of that, A omega cosine omega t plus phi, and then A is the derivative of that. And then you're going to have the omega is the same thing, k over m. So that part is the same. So the only difference is that it has a certain stretch amount to begin with. Okay, now whatever holds true for x, v, and a also holds true for q, I, and di dt. Let's see. Qi di dt. So in this circuit, with a battery, the equation will be Q. So then I'm just going to take this equation, replace mg over k by VB, CVB, right? So remember, mg gets replaced by VB, 1 over k gets replaced by spring constant. So CVB plus a sine of omega t plus phi. Then I'm going to take the derivative of that. I of t is a omega cosine omega t plus phi di dt negative a omega squared sine of omega t plus phi. Okay, then omega is going to equal square root of, what was the other one? K over m. But now I'm going to replace that by what? M gets replaced by L. And then K gets replaced by 1 over C. So that's the natural oscillating frequency of an LC circuit. So it's oscillatory motion. This is acting like a spring. This is acting like a block. Now notice the inductor looks like a spring, but it's actually, in a Physics 101 scenario, it's acting like a block. So it's more like this guy. The inductor is more like this guy. You see? The capacitor is the one that's acting like this, like the spring. So the capacitor stores energy by the charge that you place in there, right? And then this stores energy by stretching it or compressing it, you see? So that's the capacitor and the spring are the same. But a block hates changes of velocity. That's why the block has inertia. It doesn't like velocity to change. Just like an inductor doesn't like current to change, you see? That's why the inductor behaves like the block. Inductor hates changes of current. It resists changes of current. just like a block resists changes of velocity. You see. So then the other guy that doesn't have a battery is very similar. It just oscillates back and forth. It's just like a block on the horizontal surface. So then you just have Q of T. AW cosine WT plus phi di dt. Okay.